Now let's look at the third phase where we compute the effective address. Phase 3 is compute effective address. Okay, so this is the phase where we compute the effective address of the operand. And now we need not compute the effective address of the operands always. It is not required for all the instructions. Only for few instructions it is required. And what are the types of instructions? We have already seen this in the last video. Just see this. Depending on what the decoder is going to show, the output of the decoder, it can be either D0 or D1 or D2, so on, D7, right? So D0 to D6, we have already decided that these are all memory reference instructions, and if it is D7, they are either IO related instructions or the other one is register related instructions. Therefore, if D7 is 1, we need not execute this phase at all. We can skip this phase and we can directly go to the execution phase. Therefore, remember this, all the instructions need not go through all the phases, even though we are listing down the phases in the instruction cycle. This point is very important when we come to the pipelining. So what is it? All the instructions need not go through all the phases, even if we are having all the phases listed. Got it? So in this case, only the instructions which are having either D0 or D1 or D2, one of them as active, is going to perform memory reference. Even in those memory reference instructions also, all the instructions need not calculate effective address. So if you remember, while decoding the instruction, we did three things. We have sent the 3 bits, see, 15th bit of the IR, we had send it to the I, which will say the mode, and then in the IR 14, 13, 12, they are sent to the decoder, isn't it? And now the remaining, which means in the IR, all the bits from 11 to 0, the 12 least significant bits have already been loaded in the address register. So in case if I equal to 0, it means direct address is given. In that case, effective address need not be computed, because effective address is already present in the AR, right? In case if it is indirect address, which means if I equal to 1, it means that the indirect address is provided. So how to identify all these cases, how to separate them out? Just use the conditions whichever whatever you can see there. So now how to separate them is depending on D7. If D7 is 0, I can write like this. This means that D7 is 0. If D7 is 0, right, and if I is 1, I can write like this. And what about the clock cycle? T0 is over. If you remember this, clock cycles T0 or the timing signals T0, T1 are dedicated for fetching, right? And then T2 is dedicated for decoding. Now we are at T3, right? So if it is a memory reference operation, which means D7 prime, and if the address given is indirect address, and if you are currently in the timing T3, timing signal T3 is running, then we are supposed to compute the effective address. How are you going to compute the effective address? Simple. Whatever is present in the address register, okay, we have to send it to memory and read that from memory into AR. This is the signal that I have to implement, or this is the action that I need to take. Are you understanding this? Whatever is present in AR, I have to send it to memory, and there the actual address will be present. I hope you remember how the indirect address is working, right? So indirect addressing means, let us say instruction is AR is containing 100. Then we have to get the address which is present there, and this number has to be loaded. Therefore we go to the memory which is pointed by AR and load that whatever is present into AR. Alright, So how can we implement this? So simple, we are going to have a AND logic, right? So AND gate, to the AND gate I am going to give one is D7 prime, which means D7 will be applied here, and the other is I flag, and the other is T3. These three are applied, and now depending on this particular signal will be used to enable this action. Got it? So how to enable this action? First we'll open that, select this AR, so that AR will first we'll select the memory, and then AR is already connected to the address of the memory, so we'll read from memory, and at the same time we enable the load input of AR. We enable two things there, right? So if you have the memory unit here, we'll enable the read input of the memory, right? And along with that, to the signal, to the bus, we are going to give 1 1 1 through the OR gates only. Anyway, it is going through OR gates only. Okay, I'm just showing you rough diagram, and this is going to select the memory output onto the bus. So how will the memory know that it has to read from AR? Already we know that AR is connected to address of the memory, right? So address bus is already there, it is always connected. Therefore whatever is present in this 100 will come on to the bus. So once it comes on to the bus, we have to give it to AR. How can we give it? Every register is going to be connected to the bus, right? So we have to enable the load. So we take this load. So using these connections we can implement this action. Got it? Now what if I is not 1? What if I is 0? Which means the instruction is memory reference instruction itself. Okay, and now I is 0. So if I is 0, I am just writing this I prime, and now if the timing signal is T3, what does this mean? It means that the instruction is memory reference and the address given is direct address. So when the direct address is given, we need not do anything at all, nothing, which means for this type of instruction, when this is the condition hit, T3 is completely wasted. So in other words, it is called as stall. Stall means STALL, stall means we are not doing anything, we just leave it, right? So actually there are two strategies here. Instead of leaving it, you could directly go on to the next phase, execution phase, but then I intentionally leave. The reason is simple. See, now the instruction, these two instructions are actually same instructions, right? Memory reference instructions. And now if I start for one type of instruction, if I start execution here, and for the other type of instruction if I start executing at T4, then what happens is I have to have two different hardware for both the types of instructions separately. Even though the action is same, we might end up doing more work. So that is why I'll just hold it for some time, so that next time without looking at I at T4, I can just do the action required, right? Depending on what type of operation it is, I can do the same. So from the next time onwards, I need not check I. If I wait for one cycle here, I need not check for I again. That is the reason I want to wait. And some people say that, why do you want to wait? Why do you want to waste a timing signal? You can go ahead. But then in our computer, we are just waiting. So that is called as stall, right? So which means in this one we are just simply waiting. So if you see this, our instruction cycle is going to contain, one is instruction fetch, and other is instruction decode, and the other is calculate the effective address, and the next one is execute. Got it? And what is the in this type, we are simply not using this. Got it? If this is the instruction, we are not using this. Okay, and now for the next type of instructions are, what if D7 is 1? So these are two types of instructions we have seen, and the next type of instruction is, what if D7 is 1? So what does it mean? Either it is a register reference instruction or it is a IO related instruction. How can we distinguish them? Depending on I. If I is 1 and if the cycle is T3, then we know that this one is related to IO. Right? So we can start execution. Here I am not going to wait, I am directly starting execution, right? execute the IO instruction. So how to execute it, we shall see it later. So for now, what is happening here is, if it is an IO type of instruction, we are completely avoiding this, and for that instruction we are directly doing this: fetch is over, and then decode is over, and directly we are going for execution. Got it? So it has taken T0, T1, it has taken T2, and it has taken T3. In T3 we are directly executing, right? And now if you see this other type, if D7 is 1 and if I is 0 and if it is T3, it means that it is register reference instruction. And here also in register reference instruction, we need not compute any memory, we need not compute any effective address at all. So there also I am going to execute. Got it? So if you observe this, the instruction cycle is also changing depending on the type of instruction it is, right? So what is happening here? So just watch it. Now instructions are of 3 types, basically 4 types, but initially 3 types. Okay, so first one is memory related instruction, this register related instructions, and IO related instructions. And also memory related instructions are also of 2 types. One is direct reference and other is indirect reference. In case of indirect reference, we have fetch, we have decode, and we have this phase as well: compute the effective address and then execute. Therefore I am going to use T0 and T1 here, and T2 here, and T3 here, right? And in case of this direct reference, we are going to have fetch here, decode here, and we are not doing this compute effective address, but still we are not starting the execution there, therefore we are not using it. So even though we are having an opportunity to start executing here, I am not going to do anything, I am just going to sit idle. So it is called as stall, right? And then both of them are going to start executing at the same point. Now coming to this register reference instruction, we simply have fetch and then this decode, but then we are not going to worry about we are directly going into the execution of the instruction. Therefore we effectively have only 3 phases for this instruction, right? So what happens is, execution of register related instructions will finish faster compared to the other these 2 instructions. Similarly for IO also we are doing the same: we fetch, we decode, and then we execute. We need not wait for the computing the effective address. Got it? And in most of the other computers, what they do is, even this execution phase also they will break up into 3 phases. One is fetch operand, perform operation, write back. But then just to keep the thing simple, I combined all these 3 and I put it here. Later I'll show you in pipelining what are the other things that we can do here. But let's see the simplest one first. You understood this one, right? So what is this phase going to do? This phase is not useful or used in all the types of instructions. It is used only in memory related instructions, and that too indirect address specified memory related instructions. Indirect, it is simply a stall. Got it? And now what are the things that we have finished? So coming to the memory related instructions, we have finished timing signals T0 and T1, right? What did we do here? We fetched the instruction, and then we have finished timing signal T2. What did we do? Decode here. And then we have finished timing signal T3. What did we do? Compute the effective address of the operand. Then coming to IO or register related instructions, we have used up only T0 and T1, which is fetch, and then we have used up T2, which is decode, and now T3 is not yet used, and from T3 I will start the execution. I will show you how it is done. Therefore execution of memory related instructions will start at T4, and the execution of IO or register related instructions will start at T3, and the delay is nothing but it is used up for computing the effective address of the operand. Got it? Okay.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.